Hey everybody. Today we're doing a couple of entry-level related rates problems. Here are the two that we're going to do. They're both pretty typical of problems that you see in Calculus 1. Problem 1. A large spherical balloon is being inflated at a rate of 6 cubic feet per minute. How fast is the radius of the balloon increasing when the volume is 30 cubic feet? Just philosophically, it stands to reason that we ought to be able to compute this. We know that radius and volume of a sphere are related, right? The volume is 4/3 pi r cubed. And we're given the rate of change of the volume. So it stands to reason that we ought to be able to compute the rate of change of the radius. Whenever you're doing a related rates problem, your first step should be to explicitly identify the rate that you're given and the rate that you need, and to write them down as derivatives. Here, we need the instantaneous rate of change of the radius with respect to time, so dr dt, and we need it when the volume is 30. We're given the instantaneous rate of change of the volume, dv dt. That's going to be 6 cubic feet per minute. Next, we want to write down a relationship between the two variables being differentiated here. So a relationship between v and r. Depending on the related rates problem that you're doing, this relationship could come from some geometric formula, physical dependence, or it could just be an equation that you're given. In this case, we have that volume formula. 4/3 pi r cubed is the volume of a sphere. Now, both v and r are functions of time. As time elapses, both volume and radius are going to be increasing in this case. So let's explicitly note that in our equation, just this once, since we're just getting started. The big idea now is to differentiate the entire equation with respect to t, to get some derivatives into the game. The subtlety here is that on the right-hand side, we have a composition. We have a function inside a function. R of t sits inside the cube function. So when we differentiate that right-hand side, we're going to need a chain rule. Overall, the result is dv dt is 4 pi r squared dr dt. Already you can see you have a relationship between the two derivatives that I'm interested in here. In order to finish this problem, we're going to substitute in the values that we were given and hopefully solve for dr dt. So we know that dv dt is 6. In order to finish this problem, we're going to have to determine the value of r for which v is 30. So we have to go back to our original equation, the volume formula for a sphere. We have that v is 30. We're going to plug that in and then solve for r to find the radius when v is 30. In this case, we get about 1.9 feet. Now we really are ready to finish the problem. Going back to the relationship that I have between the derivatives from the previous slide, dv dt equals 4 pi r squared dr dt at v equals 30. And plugging in r when v is equal to 30, that is the cube root of 90 over 4 pi, about 1.9 feet. And solving it for that dr dt, I get about 0.13 feet per minute. That's the rate at which the radius of this sphere is increasing at that point in time. Problem 2. A point moves along the graph of the function y equals x minus x squared. Find dx dt when x equals 1. Find dy dt when x equals 1 if dx dt is 2 at that point. Assume t is measured in seconds. So we know the instantaneous rate of change of the y value along this curve. We'd like to determine the instantaneous rate of change of the x value. So in this case, we're given a lot more than in the previous example. We're explicitly told one of the derivatives, namely dx dt when x equals 1. That's going to be 2. And we're explicitly told the derivative that we're supposed to be trying to find, dy dt when x equals 1. We need a relationship between x and y, yes, but actually we're given that, y equals x minus x squared. So really all we have to do is to view that in the context of having y and x both as functions of t, and to differentiate the entire equation with respect to t. Doing that implicitly, I get dy dt equals dx dt minus 2x dx dt. The last term on the right there, dx times dx dt, is coming from a chain rule. We have x of t sitting inside of the square function. Now we can solve for dy dt just by plugging in the values that were given. Here we know that x is 1 and dx dt is 2. Overall, when the x value of the point is 1, the y value is decreasing at a rate of 2 units per second.